Hello, everyone. My name is Casey Wagoner, and I am a professor at North Carolina State University. And today I'm here as part of the CMBS4 collaboration to talk about dark energy, which is one of the many interesting topics in cosmology. Dark energy is a very interesting topic that we'll explore today. But as we do that, this talk is going to be a little bit different. Is going to be different in the sense that I can't really tell you what we do know, and that's mostly because there's a lot we don't know. What I can tell you is what we don't know. And more importantly, I can tell you what you can discover in the future. Uh, it's an interesting time to be part of this because we are really at a stage where there's a lot that we don't know about our universe, and particularly there's almost nothing that we do know about dark energy. And that means that we're really smack dab in the middle of the scientific process. And so what I want to do is just take a second, pause the video, and answer this question. Okay, great. Now that you've had a chance to do that, I want to talk about the scientific process as I think about it. First, it starts with some sort of observation. You make an observation of something, and then you want to set out to understand that. So what you do is after you observe some interesting phenomenon, you go back and you take some more observations. You look at it a little bit more, trying to look for some sort of pattern that you can identify. And then after you find this pattern, or you then develop some sort of proposed explanation for this pattern. This is often called a hypothesis. And now that you have your hypothesis, you set out to do more experiments to test this hypothesis. And for each one of those experiments, your hypothesis had a very specific prediction about the outcome of the experiment. And then the idea is you do that experiment and you evaluate the results of your experiment, and you assess how well those results align with your prediction and what that means for your hypothesis. So if the results of your experiment match what you predicted, then that gives further evidence for the hypothesis. However, if the results of your experiment don't match your hypothesis or don't match your prediction, that means that likely you need to refine or in some cases completely change your hypothesis. And so we're here, we're kind of in the middle of this, somewhere between steps 3 and 5. As you do it, as science progresses, we kind of get to step 3 and we go 3 to 5, and then we kind of go in this cyclic fashion where we go from step 5 back to step 3. And right now, our knowledge of dark energy is kind of in that cyclic process, working through steps 3, 4, and 5. So let's talk about that in the context of dark energy and what we mean. Just for a bit of background information, I think that you probably know the universe is expanding. And what you're seeing here is some data from a paper by 2 authors, last named Hubble and Humason. It's from the 1930s. And what you're seeing is that the data falls along a straight line, okay, which means that we have some model that kind of matches our data. But what are these data actually showing? What they're showing on the vertical axis is the velocity of a distant galaxy as it moves away. So as that is the velocity away from us here on Earth. And on the horizontal axis, what you're seeing is the distance of that galaxy from us. And so what you're seeing is that the galaxies that are over here that are farthest away from us, they are moving with the fastest velocity. And the galaxies that are closest to us are moving with the lowest velocities. And so effectively what this means, if you kind of think about it for a second, I think you'll be able to convince yourself that this means that this is evidence that our universe is expanding. Things that are farther away are moving away from us even faster. And so again, this data was from the 1930s. And so this shows that we've known for quite a long time that our universe is expanding. And the fact that these data, each one of these points is very close to the line, the best fit line, that gives us a lot of confidence that that's a reasonable thing that our data match this idea that our universe is expanding. So now I want to move on to the next thing, or the next step, and that is some observations of what are called type 1a supernova. Now, a supernova is an exploding star, and a type 1a supernova is just a very particular kind of star that explodes. And so these observations are used because type 1a supernova are pretty well understood as astrophysical events happen. So we have some observations back in the 90s. People made observations of a number of these different exploding stars, these type 1a supernova, and they got the data that are shown here. Now you see the text. It says that this was shocking, and so let me describe to you why. What you're seeing here is a plot that is very similar to that first plot that I showed, and effectively what you're seeing is on the horizontal axis, it's talking about the horizontal axis is how fast this star was moving away from us. And the vertical axis is how far away from us that thing is. So the vertical axis is the distance to the exploding star. The horizontal axis is how fast that exploding star is moving away from us. And, so what we would expect based on the previous data we saw was that all of these exploding stars, each blue dot, should fall along a straight line. And that's what you see. But what was shocking was in the 90s, when people made these measurements, these red data, they started measuring stars that were exploding stars that were farther away. And it's not very easy to tell from this upper plot, but what you see on this bottom plot is the same data, just with a straight line removed. So it's all completely horizontal. And what you see is that the red data points, they seem to align with this sort of middle line, but they certainly do not align with this sort of greenish yellow line. And that greenish yellow line was actually our understanding. That was our hypothesis of how the universe behaved. And so what I would say when I look at this data, whether you say these red data points best match this sort of line that curves upwards or this line that goes completely horizontal, that's maybe questionable. But one thing you can say definitively is that they do not match this green line very much. And so what that means is that this new set of data that we took for these stars that are farther away, these exploding stars that are farther away, they do not match our hypothesis of how the universe functions. And moreover, they don't match in such a way that what it means is not only is our universe expanding, it appears that our universe is actually speeding up in this expansion. It is all of the distant objects are getting farther and farther away from us at a faster and faster rate. It's an accelerated expansion. And so that's what the text now says. The idea is that for the first time, it's not just that the universe is expanding, but there's an acceleration to this expansion. This was a shocking observation.